The permutation group S4 consists of all permutations of the symbols 1 to 4. There are 24 such permutations. The identity, which leaves all 4 symbols unchanged. Transpositions, which interchange a pair of symbols. There are 6 of these. 3 cycles, like this one, where the symbol 1 is mapped to 2, 2 is mapped to 3, and 3 back to 1. The missing symbol 4 is fixed. There are 8 of these. Then there are 6 4 cycles, which move all 4 symbols. Finally, pairs of transpositions like this one, which interchanges 1 and 2, and interchanges 3 and 4. There are 3 of these. That's all 24 elements, and we've listed them in 5 columns or classes according to cycle structure. Now within each of the classes, say within the 3 cycles, there's an algebraic way of getting from any element to any other element. The algebraic relation between G and H is going to be the main theme of the program, so bear with me while I derive it. The first step is simply to rename the symbols of G to get those of H. And when we include the fixed symbols of G and H, then the renaming operation can itself be expressed as a permutation in S4. Let's call it K. The symbol 1 is renamed as 2. 2 becomes 4. 4 becomes 3. And finally 3 goes to 1. Having found a renaming element, it's not difficult to prove that G and H are related by H equals KG K inverse. The details of the proof are covered elsewhere in the course, but it's easy to see why this relation holds. For example, the symbol 2 is mapped by H to the symbol 3. But we can achieve this equally by first using K inverse, mapping up to 1, then across to 4 using G, and finally K brings us back down to 3. When 2 elements H and G are related in this way, we say they're conjugate in S4. This idea generalizes to any group, not just permutation groups. A pair of elements G and H in a group G are said to be conjugate in G if H equals KG K inverse for some K in G. We say that H is a conjugate of G and that K conjugates G to H. In fact, the relation is symmetric because K inverse must then conjugate H back to G. So G is a conjugate of H. The conjugacy relation splits the permutation group S4 into classes, as you've seen. It classifies S4 into cycle types. But conjugacy will partition any group into classes. 2 elements which are conjugate will be in the same conjugacy class. So what do conjugacy classes look like if the group is not a permutation group?
For example, what if we take the symmetry group of this double tetrahedron? All the transformations of the object which return the object to the space that it originally occupied. We looked at this symmetry group in an earlier television program. What do the conjugacy classes look like here? For example, are all the reflections in the same class? By the end of the program, we'll have found all the conjugacy classes of this symmetry group. To achieve that, we'll use an important theorem that we'll prove later, which relates the algebraic idea of conjugacy with the geometric idea of the fixed points of each symmetry. But let's look first algebraically at conjugacy in a simpler group. Recall the symmetry group of the square. It has 8 elements, the identity and 3 rotations, and 4 reflections. To find out how this group partitions into conjugacy classes, let's consider all possible conjugates. Instead of looking at a Cayley table, we'll make up a conjugacy table. There are 8 elements G to be conjugated, and for each G there are 8 elements to conjugate by. For example, this entry will be the element T, S, T inverse, which turns out to be U. And the rest of the table looks like this. So, for example, the element S turns out to be conjugate only to itself and to the element U. And U is conjugate only to U and S. So S and U are in the same conjugacy class. And no other element belongs to that class because no other element conjugates to either S or U. Similarly, R and T are conjugate and no other element is conjugate to them. So R and T form a second conjugacy class. And the rotations subdivide into 3 conjugacy classes. The identity is conjugate only to itself, so E is in a class of its own. And so is B, as it happens. But A and C turn out to be conjugates. So the group is partitioned into these 5 conjugacy classes. Now that we've got all 5 classes, let's see what they look like geometrically. Take the reflections. Geometrically, there are 2 types of reflection. Those in the diagonals of the square, S and U, and reflection in lines bisecting opposite sides, R and T. So there are 2 geometric types, and they coincide with the 2 conjugacy classes. Let's see if the same thing happens for rotations. We've got these 3 classes. Is that what we'd expect geometrically? In fact, we have rotation through 0, a quarter of a turn, half a turn, and 3/4 of a turn. So it's not surprising that the 0 and half turn are in separate classes. But what about the quarter and 3/4 turns? Well, 3/4 of a turn has the same effect as a quarter of a turn in the opposite sense. So there is a geometric resemblance between A and C.
So we've seen that conjugacy appears to bring together elements of the same type. In this case, elements in the same conjugacy class are of the same geometric type. And in S4, conjugate elements have the same cycle type. That's 2 quick examples. Let's now look at our main example.
The symmetry group of the double tetrahedron. Let me quickly remind you what the symmetries are. There are 6 direct symmetries. The identity, then 2 rotations about the central vertical axis, and there are 3 rotations like this one, rotation through pi about a horizontal axis. Then there are 6 indirect symmetries. These can be obtained by composing each of the direct symmetries with 1 indirect symmetry, say this one, reflection in the central horizontal plane. That will give us this reflection itself and 3 reflections like this one in vertical planes, and 2 further indirect symmetries which are compositions of this reflection with a rotation either through 1/3 or 2/3 of a turn. So, how does this group of 12 symmetries subdivide into conjugacy classes? Well, the way we've illustrated the symmetries is in terms of the geometric type. Each of these 6 models represents 1 geometric type. Will conjugate elements fall into these same 6 classes? To find out, we could try what we did earlier and work out a conjugacy table, which would have 12 by 12 entries. That's 144 calculations. But there's a simpler way. First, let's represent each symmetry as a permutation of the 5 vertices. So, for example, this reflection transposes vertices 1 and 2, and this one transposes vertices 4 and 5.
Here are the 12 permutations representing the symmetries. The direct symmetries on the left, and composing each with 4, 5, the indirect symmetries on the right. And we've added dividing lines to separate the 5 distinct cycle structures. This subdivision must take us some way towards classifying into conjugacy classes, because we know that for 2 permutations to be conjugate, they must have the same cycle structure. More than that, this is very nearly the geometric classification that Ian described just now. For example, the 3 pairs of transpositions are of the same type geometrically. Rotations about horizontal axes. But the subdivision doesn't quite match our geometric classification. Consider the 4 transpositions. The first one, 4, 5, represents reflection in this horizontal plane. But the other 3 transpositions represent reflection in 3 vertical planes. So the first transposition represents a geometrically different type of symmetry from the other 3. So perhaps the element represented by 4, 5 is not conjugate to the other 3. Perhaps it's in a separate class of its own, as indicated by the dotted line. But is this possible? Can we have elements of the same cycle structure in different conjugacy classes?
In fact, that happened earlier, but we didn't point it out. If we label the vertices of the square, then each of the 8 symmetries can be represented by an element of S4. For example, the rotation B transposes vertices 1 and 3 and transposes vertices 2 and 4. But the reflection T also performs a pair of transpositions. So B and T are represented by permutations with the same cycle structure, a pair of transpositions, yet they fall into different conjugacy classes. How can that be? Well, in the group S4, B and T are conjugate. But in S4 we have 24 conjugating elements to choose from. In this subgroup of S4, we have only the 8 elements to conjugate by. And as we've seen, T is not one of the conjugates of B.
So it happened with the square, and it may happen here, that 2 elements with the same cycle structure are not conjugate. So these boxes we've drawn may subdivide further. For example, the dotted line may be a genuine division line between conjugacy classes. How do we find out?
Let's first get a feel for the situation by using our models to calculate a typical conjugate. Take this rotational symmetry, which I've called R2, because vertex 2 is on its axis of rotation. It transposes vertices 1 and 3 and vertices 4 and 5. Let's conjugate it by a particular element K. Rotation through a third of a turn about the vertical axis. I'm going to perform the triple composition K R2 K inverse on this model. And I want you to keep an eye on what happens to this axis. I have to apply K inverse first, and I'm particularly interested in this axis because it's the axis which K inverse moves to the fixed axis of R2. Let's call that axis 2. So here goes. First, I apply K inverse, which moves this axis to axis 2. Then R2 leaves each point on it fixed because it rotates about the axis. Then K moves it back where it started. So K R2 K inverse fixes this axis. Every point on this axis is back where it started. Now here's the important point. What is special about this axis is that it's K of axis 2. Axis 2, K of axis 2. In fact, this will happen whatever K we choose. R2 fixes axis 2, and K R2 K inverse will fix K of axis 2. In fact, there's nothing special about R2. All conjugates behave like this. We can express this as a general theorem.
Let G be the group of symmetries of any set of points x. For For example, X could be the set of points which make up this solid double tetrahedron. And let H be the conjugate of an element G by an element K. The theorem says, if G fixes a point X, then H fixes K of X. And conversely, if H fixes a point Y, then G fixes K inverse of Y. The proof goes like this. The first half of the theorem can be illustrated with this diagram. The 4 patches are 4 copies of the set capital X. Along the top we've illustrated that G fixes the point X. G maps X to X. Then mapping downwards with K, we consider K of X. And the theorem claims that H maps K of X to K of X. Is this true? Well, H equals K, G, K inverse. So to see what H does to K of X, we apply K inverse first, which takes it to X. Then G, which leaves it at X. Then K, which takes it to K of X. So H does fix K of X. That proves the first half of the theorem, and the converse follows immediately from the fact that conjugacy is symmetric. If K conjugates G to H, then K inverse conjugates H to G. So whatever theorem we prove concerning K conjugating G to H, the result holds equally for K inverse conjugating H to G. Therefore the converse holds. It's illuminating to interpret this converse in terms of our diagram. We just have to start at the bottom and read upwards. If H fixes the point Y, then applying K inverse, the image of Y is fixed by G. So that proves the theorem. And because it works both ways, we can conclude that K maps the set of fixed points of G one-to-one onto the set of fixed points of H.
Well, knowing the set of fixed points of a symmetry goes a long way towards identifying it. We can now identify all the conjugates H of R2. Axis 2 is the set of fixed points of R2, and the theorem tells us that for any K, not just this one, K R2 K inverse has K of axis 2 as its fixed set. So what can K of this axis be? That is, where do elements K of the group take axis 2? We've already seen that this K rotates it to here. Other elements K, like the identity, leave it where it is, and others, like the opposite rotation, take it to a third position. And those are the only 3 possibilities. All symmetries K must map it to one of those 3 positions, because this central triangle must fit back in its original space. So the conjugates of R2 fix this axis, or this one, or this one. But the only symmetry which fixes an axis like this is rotation through pi. So we know all the conjugates of R2. As we predicted, R2 is conjugate to itself and to the other 2 rotations of the same geometric type, and to nothing else.
That confirms this conjugacy class. Let's now move straight away to the 4 transpositions. Is 4-5 really in a class of its own?
Well, 4-5 represents reflection in the horizontal plane, so it fixes all the points of this plane. So any conjugate of 4-5 by a symmetry K will fix K of this plane. That is, it'll fix another plane, and so it'll be a reflection. But which one? Well, there's no symmetry K which maps this horizontal plane to a vertical plane. So no conjugate of 4-5 can be a vertical plane reflection. In fact, every symmetry K maps this plane to itself. So the fixed set of every conjugate of 4-5 is this plane. Therefore, every conjugate is 4-5 itself.
That confirms our conjecture that 4-5 is in a conjugacy class of its own. Let's now look at the remaining 3 transpositions.
1, 2, which I've called S3, is reflection in the vertical plane through vertex 3. So if we conjugate by K, we'll get a reflection in K of this plane. For example, if we take K to be this rotation, it maps the plane to this one. So K, S3, K inverse is reflection in this plane. And if instead we choose K to be rotation in the opposite direction, then K, S3, K inverse is reflection in this vertical plane. A reflection in a vertical plane is the only thing we can get. Whatever symmetry K we choose, it maps the fixed plane of S3 to one of the other two vertical planes or to itself. So these three reflections form one conjugacy class.
As expected. What about the identity?
Well, that fixes every point of the figure. But for any conjugating element K, K of the whole figure is the whole figure. Therefore, the identity can only be conjugate to symmetries which fix the whole figure. And the only symmetry which does that is the identity itself.
So the identity is in a class of its own. That's obvious algebraically anyway. K, E, K inverse must be E. The K and K inverse cancel. Next, let's consider the two 3 cycles. Are they conjugate to each other?
Both represent rotations about the vertical axis through 2 pi by 3. 1, 2, 3 this way, and 1, 3, 2 the opposite way. So both rotations fix the vertical axis. Now every symmetry K maps the vertical axis to itself. Therefore any conjugate of this rotation fixes the vertical axis. So the only possible conjugates are itself and the other rotation about the vertical axis. Well, can we find a symmetry K that conjugates this rotation to the other one? In fact, 6 of the symmetries do. This is one that does so. I'll leave that for you to confirm afterwards.
So the two rotations in the vertical axis are conjugate. Finally, the two composite symmetries. Are they in the same conjugacy class?
We have this reflection combined with a 1/3 rotation, either this way or the other way. Well, in fact, these two have the same fixed point set. Each of them fixes only the central point where the axis and the plane meet. So they might be conjugate to each other, but to nothing else, because every other symmetry fixes at least a line of points. And just as with the vertical rotations, there are 6 elements K which conjugate one to the other.
So now we've confirmed all the 6 conjugacy classes that we suspected on intuitive geometric grounds.